Hello and welcome to another video on C-star algebras from a novice perspective. And today we're going to talk about the Gelfand Transform, and our main goal is to prove the Gelfand Representation, which is actually a theorem even if it's not called a theorem. So many people would call this the Gelfand Representation, which is both a representation of C-star algebras in a certain way, and it is also a theorem. But I've been calling it the commutative Gelfand theorem in the past, so this might be a source of confusion. And I certainly was confused by this naming convention of this theorem in the past. But before we go on to do that, I just want to have a quick recap of what we've been doing in the last lecture. And that was we considered abelian Banach algebras A, and we considered characters on these algebras. And these are non-zero multiplicative linear functionals. And if phi is a character, then I noted in particular that phi evaluated at A is always in the spectrum of A, for any character in any element A in the algebra. And then when we considered the set of characters of A, which we denote in this way here, then this is a locally compact and Hausdorff space in the weak star topology. So we didn't use the norm topology or anything, we used the weak star topology to really prove that this set here is locally compact and Hausdorff. And then we noted that it is compact if and only if the Banach algebra A that we started with is unital. And otherwise it's just locally compact, but not compact. And then if A is non-unital, then we consider the unitization, because then this space of characters on A is canonically homomorphic to the set of characters on A tilde, the unitization, minus one specific character phi sub 0, where phi sub 0 is simply the character whose kernel is the entire algebra A. So phi sub 0 of A plus something times the unit is equal to this something lambda here. And with this in mind, with this fresh in mind, we can go on and define the Gelfand transformation. So let A be any element of the algebra. Then we define the Gelfand transform A hat of A as the following expression here. So A hat of an element phi in the set of characters is equal to phi evaluated at A. In other words, we see that the Gelfand transform sends an element A in the algebra to a function A hat, which has a domain which is the set of characters here. So we see that A hat is a function with a domain being the set of characters. Now, since the topology on the set of characters is the weak star topology, we can even say a bit more. So we see that A hat of a sequence phi n, which weakly converges to phi, then it's equal to phi sub n of A by definition, but this tends to this limit because we have a weak star convergence. And therefore we see that any sequence of characters here, if that tends to a value in the set of characters, then naturally this A hat of phi sub n will tend towards A hat of phi. So in other words, we see that this set function A hat is always going to be a continuous function. And this is actually not the entire story. There are some more things to note about the Gelfand transform. And one of the most useful facts is the following theorem: that the Gelfand transform is a contractive algebra homomorphism of A into the set of continuous functions vanishing at infinity of this character space of A. Now, the image algebra separates the points of the character space. And this might seem like a technical point, but it is one small little key detail that we will need in a proof later. So I just wanted to bring it up here as well. And let's look at how the proof of this theorem go. So as we saw previously, of course, this A hat is always going to be continuous. Now, in the non-unital case, we of course go over to the unitization. So we note this canonical homomorphism between the set of characters on A and the set of characters on A tilde minus this character phi 0. Moreover, we noted that since if A is in the algebra, A, then it lies in the kernel of phi 0. So then A hat of phi 0 is equal to phi 0 of A, which is just equal to 0 for every A in the algebra. And therefore, from this we can see that, in fact, this function here, A hat, must lie in the set of functions which vanish at infinity of this set. And that is because, as I've said before, this set here is the one-point compactification of this set over here. So if this set here is locally compact, and this set is the one-point compactification, and then you have that these functions here vanish at this particular character, well, that is basically just saying that they vanish at infinity. And then we have that the Gelfand transform is contractive as well. And this is simply because the norm of any character is equal to 1. And since this norm on this algebra here is just the supreme norm, this result follows very easily. So let's say that we look at this expression here, and we want to calculate the norm of A hat here. So the norm of A hat must be equal to this phi. And now I'm not really considering phi to be this phi 0, but just any phi, really. Then this would be equal to this expression here, but phi of A, no matter what A is, this expression can never have larger absolute value than the norm of A. So that's why we see quickly that it's a contraction. And now we finally note this little detail about separation of points. And that is that the image of A under this Gelfand transform, which I will denote in this way, I just set hat on the entire algebra A. This separates the points of the character space. And what I mean by that is simply that if phi 1 is not equal to phi 2 in the set of characters, then there must be an element A in the algebra such that A hat of phi 1 is not equal to A hat of phi 2. And this is just because these points, phi 1 and phi 2, correspond to distinct characters on A. And just look by definition, you must be able to find an element A where these two characters disagree. That's it. So it's not a very difficult statement to prove, but it is important, and it has some useful consequences. And one of them is the following, which we are also going to need when we want to prove our main theorem. And it's this corollary that if A is a unital Banach algebra, which is commutative, of course, then an element A is invertible if and only if A hat is invertible as well, which is precisely when A hat does not vanish on this set of characters here. And therefore, we have that, excuse me, the spectrum of A is equal to the spectrum of A hat. And the spectrum of A hat is, of course, just the range of A hat. And thus we can conclude also that the spectral radius of A is just equal to the norm of A hat in this supremum sense. And now, before I go on to the proof, I just want to sort of compare this statement to another one which I made in the video about spectral theory. And that is that if we have a C-star norm on A, that is, if A is a C-star algebra with a C-star norm, then the norm of self-adjoint elements will just be their spectral radius. And therefore, the norm on a C-star algebra is actually intimately tied to the spectral radius. And this is also something that is going to come back later on in this video. So I just want to bring it up and look at this contrast here. So the Gelfand transform, well, the norm is always going to be tied to the spectral radius. And then when we talk about C-star algebras, well, we have a norm that is intimately tied to the spectral radius again. So we're going to see this play out later on. But let's now prove the statement that the spectrum of A is equal to the spectrum of A hat here, and everything that this statement says. And first off, if A is an invertible element, then since the Gelfand transform is a homomorphism, we have, of course, that the hat of A inverse must be the inverse of A hat. That is, by definition of a homomorphism, that must be true. Conversely, if A is not an invertible element, then the ideal, which is the closure of A times the entire algebra, so it's basically the principal ideal generated by A, then this is a proper ideal, and thus it's contained in a maximal ideal M here. Now note, when I say that it's a proper ideal, that's because I assumed that my algebra A was a unital algebra. Otherwise I couldn't say this necessarily. Now, let phi sub m be the associated character with the kernel being m here. Then, of course, A hat of this character must be equal to phi sub m of A. But A lies in M, and M is the kernel of phi, so this is equal to 0, which implies that A hat is not invertible in this algebra of functions. And then we have proven sort of the first part of that corollary. And from that, we easily see that the spectrum of A must be equal to the spectrum of A hat as well, which naturally coincides with the range of A hat. And then, since the norm in this function algebra is the supremum norm, and the range of A hat is its spectrum, then of course the spectral radius must be equal to the supremum norm of A hat. There is no other way. So it's just a natural consequence of these spectrums agreeing and the fact that the range of A is the spectrum of A. And now we have this corollary, we can get to the main theorem, which is the following. That if A is an abelian C-star algebra, so a bit stronger condition now, then the Gelfand transform is in fact an isometric star isomorphism from A to the set of continuous functions vanishing at infinity defined on the set of characters on A. And this is the most important theorem in this video series so far. And as we shall see in later videos, it has some huge ramifications for the general theory of C-star algebras. So how do you actually prove this theorem? Well, you have to break it down in smaller cases. So first off, there are two separate cases which are kind of obvious, and that is the unital and the non-unital case. And in the unital case, we divide the statement into three lemmas. So we begin with the first lemma, which states that the Gelfand transform is a star homomorphism in this case, and the second one stating that it is an isometry, and the third that states that it's a bijection. And then once we have proven the statement in the unital case, we treat the non-unital case, and that one is resolved by considering the unitization. So let's get straight to proving this theorem, beginning with lemma 1 and then going forward. So the lemma 1, which is to prove that the Gelfand transform is a star homomorphism, is actually the most technically involved one, I think, of these three, or at least it is the longest one by far. But realize that we only need to prove that phi of A star is always going to be equal to the complex conjugate of phi of A. That is what we need to prove, because then we can also prove that this Gelfand transform automatically preserves the star structure and thus becomes a star morphism. And this thing is easiest to do by first considering the case where A is self-adjoint, which we have here. So let's do that and form this family of unitary elements, which we denote by u sub t here, which we define to be e to the power of I times t times a. Now, this expression here, this exponential function is of course well defined as this power series here. And this power series is absolutely convergent, so there's no issue whatsoever. We can define this element, no issues whatsoever. And then we can check that this really is a unitary element for all t, which is easy to do since A is equal to its own star here. So ut star is just the sum of all the stars, because the star operator is of course linear in that, or it's skew linear in, or whatever, and you can basically do it like this. You take the star of every element like this, so you get this expression here. That is, you take the star of these terms, and since a star is equal to a, we get that this is in fact by definition equal to e to the power of minus I times t times a. But this is just the inverse of what we started with. And this is something that, of course, you need to check it, you need to know it, you need to know the complex exponential function in the case of general Banach algebras, but this is a well-known result, that the inverse of ut, u sub t here, or the inverse of this guy, is simply this element here. And from this we can use the C star property to deduce that the norm of ut squared is equal to this expression here. So this is a C star property. But this element here is just equal to 1, because ut star is the inverse of ut. And therefore, the norm of this whole thing must be equal to 1. And from all of this, we see that it's a unitary element and everything works well. But now, since the norm of this element is equal to 1, we start using the properties of phi as a character. So phi, being a character, means that it's a contractive norm, or it's a contraction. So it has norm equal to 1 here. And that means that the norm of phi of ut, u sub t, must be less than or equal to 1. Let's do some calculations now, because this can be calculated explicitly actually. So we just factor everything out. And since phi here, it's a multiplicative linear functional, or it's a character, we can take it term by term in this power series. So we get that this expression here must be equal to this expression here. But this expression is by definition equal to e to the power of I times t times phi of a. But the absolute value of this is just the real part, e to the real part of this expression up here. But that real part is just minus t times the imaginary part of phi of a. Now here comes the trick, and why we actually made this family u sub t for all t here. That this inequality holds for every real number t. Therefore, this phi must be a real number, because this imaginary part here must be 0, because otherwise this expression could be positive, and e to the power of a positive number is of course greater than 1. And there we have proven our first little puzzle piece, that if we have a self-adjoint element a, then a character evaluated at a must be a real number, which is fantastic, in its own right. But now if z is an arbitrary element instead, then we let x here and y, which are defined in these ways, be the real and imaginary parts of z. Now this is a very common construction in general. This is not something we just do here. For general star algebras, you see this all the time. And it is really the real part of, or the more general analog of, the real part of a complex number and the imaginary part of a complex number. But note in particular that both x and y here are self-adjoint in the way we define them, which is going to be useful. Now, we just calculate phi of z star now and see what happens. And because z is equal to this sum here, x plus I times y, we simply get that the star of z here is just x minus I times y. And therefore, we can use the fact that phi is a multiplicative linear functional, so it's a linear functional, so that we can split it up in terms like this. And then we know that x and y are self-adjoint, so phi of x and phi of y are real numbers. So this is just equal to the complex conjugate of this sum here. But this sum here is just phi of z, by definition, because phi is a linear functional. And then we have that we take this complex conjugate and we have proven what we set out to do. Hence, the Gelfand transform of z star is equal to the star of the Gelfand transform of z for any element z in the algebra. And therefore, the Gelfand transform is a star homomorphism. And thus, we're done with the first lemma. Now, let's move to the second one. So, in the second lemma, we wanted to prove that the Gelfand transform is an isometry. So, we need to prove that the norm of an element A is equal to the supremum norm of A hat for every element in our original algebra. And now, as I previously mentioned, even in this lecture, for self-adjoint elements, this is a pretty easy statement because on one hand, we have that the norm of a self-adjoint element in a C-star algebra is equal to the spectral radius, but at the other hand, we proved in this lecture that the supremum norm of A hat is always going to be equal to the spectral radius of A. So for self-adjoint elements, this is super easy. But how do we get to more general elements? Well, let's consider an arbitrary element Z in A. Then we use the C-star property, because the norm of Z squared by the C-star property is equal to the norm of Z star times Z. And now, this here is a self-adjoint element, so we can use this fact that we had earlier to just say that these two must be equal to one another. And now we have already proved in lemma 1 that the Gelfand transform is actually a star homomorphism, so we can split it up in this way here that we have. And this is, once again, by the C-star property for the function algebra of continuous functions vanishing at 0 equal to this norm here. So we have proven that the norm of Z squared is equal to the norm of Z hat squared in this absolute sense. And then, of course, we can take square roots on both sides and we're done. So this lemma 2 is probably the easiest of the three lemmas to prove. So let's move on to the third lemma. And this one is actually a bit tricky, but more on a conceptual level. It's actually not that difficult on a technical level. So from the previous lemma, we note that the Gelfand transform must be injective because otherwise it cannot possibly be an isometry. Now we also note that the image of A under the Gelfand transform must be a unital, norm-closed, and self-adjoint subalgebra of the set of continuous functions over this set of characters, which also separates points. Now, why do we note all of these things? Remember, we want to prove that the Gelfand transform is injective and surjective. That is, we want to prove that it's a bijection. And the reason why we note all of these technical ideals, that the image of A under the Gelfand transform is a unital, norm-closed, and self-adjoint subalgebra of this algebra here, which separates points, is because this enables us to use the Stone-Weierstrass theorem, or the locally compact version of it, which states that if X is a compact Hausdorff space and S is a separating subset of this set here, then the complex unital star algebra generated by S is dense in this set here. So what does this actually mean now for us? Well, it means that this theorem implies that the image of A under this Gelfand transform is dense in this algebra here. And that is because, well, the image of this set here is actually a unital star algebra because of everything we noted before. And it's a complex unital star algebra as well. And moreover, it is a Banach algebra. It's actually a C-star algebra. And thus, since it's a dense here, and it's a C-star algebra, that means it must be a complete algebra. And all these complete algebras, well, if they're dense, then they must contain every point in the algebra. So, to summarize all of this, the Gelfand transform is a star isomorphism and an isometry. And thus, we have managed to prove the Gelfand representation in the unital case. Let us now move to the non-unital case instead. So in the non-unital case, we now want to prove that the Gelfand transform sends this algebra A to the algebra of continuous functions that vanish at infinity of the set of characters of A, or on A. So how do we do that? Well, of course we use the unitization again and again. Once we we get into trouble with not having a unit in the algebra, then we can always find the unit in the unitization. And we note that in this case, A will always be a maximal ideal of codimension 1 in A tilde here. Moreover, as we noted before in this lecture, the set of characters on A is canonically homomorphic to the set of characters on A tilde minus this character which has A as its kernel. Now, I've said it before in the video on unitization, but if A here is a C-star algebra, then A tilde will obviously also be that. And it's also very easy to check that if A is an abelian algebra, then so is A tilde. So, if we use that, together with the fact that we have proven the Gelfand representation in the unital case, we see that the Gelfand transform is an isometric star isomorphism of A tilde that takes A tilde onto the set of continuous functions on the set of characters on A tilde. Now this Gelfand transform actually maps A onto the ideal of functions vanishing at this character phi sub 0. But this mapping is naturally, of course, identified with this, because this is something I've said before, that when you have ideal of functions vanishing at this point here, but when you think about this point, really you can think of it as the infinity point. So now we are finished. Let's just talk quickly about why this is important, and this is something we're going to see in coming videos. The reason why this is so important is because it's easy to construct commutative C-star subalgebras of any non-commutative C-star algebra as well. So it doesn't matter if you have a C-star algebra that is non-unital. It's often possible to construct these commutative C-star subalgebras. And let me just consider the following example. So say that A is a normal element of a C-star algebra A here, which simply means that A star times A is equal to A times A star. Then the C-star subalgebra, which we denote in this way, which is generated by A, is then a commutative C-star algebra, and thus we can apply this Gelfand representation that we have just gone over. And what this leads to is the idea of a continuous functional calculus of normal elements. Now, this may not seem like much, but this is a surprisingly powerful tool, and it leads to a lot of interesting consequences, which are very hard to prove if we don't use this at all. In fact, I think it's impossible to prove many of the core theorems of the C-star algebras if you cannot use the continuous functional calculus of normal elements. So, to summarize today's lecture, which was quite centered on a very particular theorem, the Gelfand transform, which we defined as the map that takes A to the set of continuous functions vanishing at infinity of this set of characters, we define it as this map here, that the hat of A evaluated at phi is just phi evaluated at A. And this Gelfand transform is a contractive algebra homomorphism for any commutative Banach algebra A. And in the particular case where A is a C-star algebra, then the Gelfand transform is an isometric star isomorphism as well. And I would like to end the video there. So in the coming videos, I will of course go deeper into the theory, but I might actually stay on the Gelfand transform and look at the Gelfand transform a bit more closely, and maybe go over an example where we don't have a C-star algebra, just to see what happens. We'll see what I make of that later on. But for now, have a good time and Merry Christmas, and let's see you in the next video.